Hello students, in this video we review the topic called linear model selection. This section uses the so-called credit dataset in the textbook, and here you have I think useful visualization of the numerical variables in this dataset. It's a good practice before you conduct your linear regression. You try to see actually what are the links between those variables. So for example, the response variables is the balance of a customer, the credit card balance. And you can see if you look balance against all the other variables, which would be here called predictor variables, age, cards would be, I think, the number of credit cards, education, not too sure how this is measured, maybe probably the years of education, income, limit on the credit card, and the credit card rating. You would look here, or equivalently, you can look here as well, because here you see balance against age is here, balance against cards is here, balance against education, and you see at least for those three, the links doesn't look very strong, but balance versus limit, for example, the link looks pretty strong, and balance versus rating is strong as well. Now you do also have the scatter plots of the predictors against each other, right? So age versus cards doesn't look like there's much of a link there, but for example, limit against rating is extremely strong, the relationship, and we'll see that this is a potential problem called collinearity, but this is for the next section, hence the next video as well. For here, what we discuss is linear model selection. So the setup is something like this. As before, you have your response variable and you have potential predictors, x1, x2, up to xp. Here we say potential predictors in the sense that those are the variables you have available to you, but they might not all be useful to explain why. So that's why we say, okay, potentially we can use them. Of course, you don't know a priori which are the ones that are going to be significant in your linear regression model. So your goal is to select the predictors that are going to create the best model, okay, and best to be defined using some metric. Now, I don't think there's a magical way to do this, but there's a few different approaches you can follow. And maybe as a comment here, one of the reasons this is not a trivial problem, and this is something you need to know. Let's say you have a certain number of predictors in your model. If you remove some, it's quite possible that the significance of the other predictors is going to change. So the p-values associated with all the predictors will change if you remove some variables from your model. And likewise, if you add some models, so if you have d variables in your model, and suddenly you add some, the significance of those initial d variables could change. And the reason for that, at least one of the reasons, is that the predictors often they're related to each other. Okay, well, I mean, this was an extreme example here, but even if they're not like super strongly related, when they're related, it could be that, well, two predictors in this example, for example, they explain the same thing, right? So if you have only one, it might be super significant to explain, for example, the balance here. But if you put two of them in your model, each of them will kind of explain the same thing, and then individually their significance might decrease. So be mindful of that. It is really the case that how significant a predictor is does depend on the other predictors in your model. And here, okay, so I said there's a few the various approaches that exist. In this specific lecture, we're going to cover what is called indirect methods in the textbook, and very related to that is the topic of subset selection. So there's a very strong link between those two things that we're going to try to explain in this video. The other methods, we're going to cover them a bit later in the course. So what is called direct methods, shrinkage, and dimension reduction. Okay, so how do we determine the best model? So in general, what you want is a low mean squared error. Remember the concept of mean squared error from the first week, but on test data. So on data that you haven't fit the model to. Now, an issue that we have is, if you recall, the training MSE is not the same thing as the test MSE. Well, yes, because when you fit your model, so you use the training data, if you overfit, if you capture trends that are not really present in the that are not real trends or real patterns in the data, it's just that you're mistaking some noise for a trend. This is called overfitting. You're going to minimize your MSE, so MSE might be quite small, but this doesn't mean you have a good model to predict other observation that your model hasn't been trained on. And this is what we call the test observations or the test data set. So again, having a low training MSE does not necessarily mean that you have minimized your test MSE. Now, there are ways to directly estimate the so-called test MSE. And we're going to cover this a bit later in the course. For example, cross-validation and using a validation set. But for here, what we call those indirect methods are simply this. We make an adjustment to the training error to account for the bias due to overfitting. So we know we have this potential of overfitting. For linear regression, overfitting is essentially putting too many variables in the model that don't really have explanatory power. But we're going to make an adjustment to the training error to correct, in a sense, this potential for overfitting. And what we do is essentially this. So we develop a few different metrics that compare different models, but we're going to see that they're not the R squared, because the R square is prone to just including too many variables in the model. So those metrics are trying to prevent overfitting. Now, to explain this a bit more, we need to make a note on this R squared, because you might say, okay, well, R squared was defined as the ratio of what the variability explained by the model divided by the total variability. So it seems to be a good metric to judge if a model is good, if it's explaining the Y using the X's. So you might say, okay, the higher the R square, the better. So that's it. I'm just going to use the R square to judge which is the best model among several potential candidates. Now, the issue is this. Well, R square is really a direct function of the training MSE. Yes, because we might write this explicitly. The training MSE, as defined in the first lecture, was, well, the average yi minus its predicted value squared, okay, with the average of that, so divided by the number, by the sample size. But you see that this is the RSS. All right, this is the residual sum squared, the top, okay, divided by n. And R square is essentially very similar conceptually. It's a function of the RSS. Recall that R square was simply defined as 1 minus RSS divided by TSS. Okay, residual sum of squares divided by the total sum of squares. Okay, so they're essentially the same thing. The training MSE and the R squared. I mean, obviously, they have the inverse interpretation in the sense that a high R squared will mean that your model is good or explaining more, and a low training MSE means that, again, your model is good because the error is smaller. Now, the fact you need to be aware of is that R squared can be somehow misleading because if you add variables to your model, R squared cannot decrease. So let's say that you have 4 variables in your model. You keep those 4, but you just add a fifth one. Even if the fifth has 0 explanatory power to explain the response, your R squared will not decrease. And this is illustrated here in the example from the book. So, and those two charts present more or less the same information, but here you have the residual sum of squares that you expect to decrease as you increase the number of predictors. But conversely, here you have the R squared that you expect to increase as you increase the number of predictors. This illustrates what I just said. Initially, okay, already with one variable, you have a decently high R squared. You add another one, okay, it increases meaningfully. Then you add another one, it increases meaningfully. But after that, you see it's plateauing, but it's not decreasing. So that's the point. Even if you add a bunch of variables that really do nothing to help you predict Y, the R squared will not decrease. So the R squared is not capable of preventing overfitting because it will never decrease, even if you keep adding variables and variables that are essentially garbage. They're not doing anything to help you predict Y. Okay, and here's the same thing, the residual that, okay, the lower the better, but it's the same thing. It's never increasing as you add variables. It can only decrease or stay constant. So here, those methods called indirect methods are modified metrics of the RSS. Okay, that we try to correct for this behavior that the RSS will not increase as you add more and more variables in the model. And in general, we don't want to have a whole bunch of variables in our model that don't explain anything. We like parsimonious models that have fewer variables that explain most of the variability in the response. Now, the first of those measures is the so-called Mallows CP. And it's defined like that. So you do have the RSS explicitly there, but then you add what you could call a penalty for adding parameters. Because again, adding a whole bunch of variables that don't do much in your model, that's not good. So because you want to minimize the RSS, if if you add this penalty that is essentially a function of the number of predictors in your model, here the D is the number of predictors in your regression model. So the penalty here is function of those number of predictors. So if you have many predictors, your penalty will be bigger and it's going to tend to increase this criteria, this new metric. And then you will not choose a model with too many useless predictors because this metric has been inflated by this penalty term. And of course, you're trying to minimize this Mallows CP. So here I should have said, you will pick, if you want to rely on Mallows CP, you will pick the model that has the lowest Mallows CP. And so again, if you have many predictors that are not very useful, the Mallows CP will increase and you will not pick those models. The second criteria is the famous Ekaike information criteria, named after this Japanese statistician Ekaike. Now, this is a very general criteria you can use for a whole host of different statistical models to pick the best model among several candidates. Now, here we have a special application of this. We use Ekaike in a specific context of linear regression. But in general, this criteria is defined like this. Okay, so this is the general definition. Again, you have this D, which would be the number of estimated parameters in any statistical model. Remember, this could be any statistical model you fitted. Okay, so D is the number of parameters, and then -2, the log likelihood of your model. So here, this big L hat is the maximized likelihood function of the model. Well, maximize, yes, because you fitted the parameters to make it as big as possible. Now, convince yourself that a low AIC is preferred. So a model will be judged to be better if this quantity is as low as possible. Well, yes, because there's a minus here. So you want to maximize the likelihood. Equivalently, you want to maximize the log likelihood, but then it means you want to minimize the negative of the log likelihood. So the smaller this is, the better. And the logic is the same as with the penalty here. You should view this 2D term as a penalty because, again, if you want to minimize this, adding a positive quantity 2D, if D is big, if there's a large number of parameters in the model, well, you make this whole thing bigger. So this is a penalty. Again, if adding parameters in the model does not lead to an increased likelihood, this whole thing is going to increase and you will not pick such models that have more parameters. So the logic is the same. You put a penalty in this criteria for adding unnecessarily parameters to the model. So you put a penalty on making the model more and more complex in the sense that it has more variables. Because again, you like parsimonious models with few variables that explain most of the trends in the data. This is the general definition of this Ekaike information criterion. But here, in linear regression, it actually completely reduces to the Mallows CP. So in the case of linear regression, those two things are absolutely equivalent. So if you want to minimize the AIC, it's the same thing in linear regression as minimizing the Mallows CP. A third criteria is also very popular, widely used, the Bayesian information criteria. Like the Akaike information criteria, it's very general, so you can use it to compare different statistical models, not only linear regression models. The general definition is given here, conceptually similar to the Akaike criteria. The only thing that changes is the penalty term. Okay, in the AIC, you had the penalty was 2D, but here the penalty is D ln n, where n is the sample size. So you see that here, the penalty is bigger because unless n is super small, D ln n will be bigger than 2D. So usually then the big BIC will give a bigger penalty for adding parameters. So in a sense, you could say this is this is a criteria that penalizes more having more parameters in the model because this part is exactly the same, -2 ln likelihood. Now, in the case of linear regression, this general criteria reduces to this to the following formula, which is quite analogous to the one we had here for the MeloCP. It is the RSS plus the penalty term. Okay, so it's the RSS plus the penalty term here, log of n. And here, all my apologies for the slight change in notation. Log of n should be viewed as the same thing as ln of n. It is the natural logarithm. Hopefully you forgive me. And here, this is the comment I told you already, that yes, BIC gives a heavier penalty on adding predictors in the model. And lastly, the so-called adjusted R-square. So the adjusted R-square, this is the one you will see in most, well, in outputs of more statistical packages, R or otherwise. And it's defined like this. So it is very similar to the regular R-squared. Recall that the regular R-squared was 1 minus the RSS divided by the TSS. And here we see my handwriting is not getting any better. Yeah, sometimes I wonder how they let me pass elementary school, but I've made it. Now compare this to this. What's the difference? Well, obviously it's the division here by this term and on the bottom by this term. And with just a little bit of simple algebra, you can rearrange and write this as 1 minus RSS, but put the n minus 1 on top. Okay, and likewise, you can put this one on the bottom. Okay, times here the n minus d minus 1. And so this should highlight that the adjusted R square will always be smaller than the R squared. Well, yes, because look at this term. Well, you will at least have one variable in your model. So this thing is going to be bigger than 1. This whole thing will be inflated then, and then you subtract something that is inflated. It's going to be indeed smaller than the initial R square. And the logic is the same as with the other metrics. You're giving a penalty for adding too many parameters in the model. Well, indeed, because if D is very big, or at least big compared to n, well, this thing was going to be substantially bigger than 1, so the R square will be reduced again by having added too many parameters or predictors in your model. Here there's a comment that this is a criteria is widely used. If you recall, we can maybe go back just to show you. I didn't lie. It is given in the R outputs. You see for this specific example, yeah, the regular R square is called multiple R square here, but then the adjusted one, you see it's a bit smaller, or actually substantially smaller in this example. I guess because n is pretty small. So this is the adjusted R square given the package. So it's very widely used, even though some might say it doesn't have as strong a theoretical foundation as the other criterias. It's not, and to my knowledge, it's not derived as like theoretical quantity. But yet it seems to work pretty well in practice, or at least it's used quite a lot. So you should know about it. Okay, so those are the four criterias, but again, the first two were equivalent in the case of linear regression. Now we illustrate this with the example again. So what is this showing? Well, simply as a function of the number of predictors in the model, well, yeah, what's the model that performs the best with those number of predictors held fixed? Meaning the model with only two predictors that performs the best as this CP, but then the model with three predictors that performs the best is here and then here and then here. And here, if you trust, it's a bit hard to see with the naked eye, but if you trust this picture, they tell you that, okay, the best model here for CP overall is the one with six predictors. But if you use BIC, you reach a different conclusion. So you reach a conclusion that the model that is the best overall is the one or is a model with four predictors. Um, I say a model because obviously if you have 10 predictors in total to choose from, well, there's many different models that will have exactly four predictors. But here we're saying among all the models with four predictors, the one with the lowest BIC has the following BIC, which turns out to be the very best model overall if you use BIC. But again, if you use something else like the adjusted R square, well, the adjusted R square, obviously you want to maximize the adjusted R square. It gives you the best model, which would be this one, I believe, with seven predictors. So you see, different criteria are a bit different. So they might give you different models. There is some agreement here in the sense that, okay, it looks like we need something like at least four predictors and no more than seven to get the best model. Okay, now here we say, okay, well, we do have valid metrics to evaluate our multiple models, so life should be easy, right? We just pick the best model. So we choose one metric, the one that maybe appeals the more to us, and then we just pick the model that has the best metric out of all the models. Well, yeah, if you can do that, great, do that. Pick the very best model. There's a bit of an issue with that, but first, we present the algorithm to, well, to get to this very best model, and it is called best subset selection algorithm. So obviously you would have a R package that would do that for you, but still conceptually, I think it's useful to explain yeah, how the algorithm works. And by algorithm, we just mean a step-by-step process that gives you the answer you want at the end. In this case, the very best model. So the algorithm is as follows. Step one, call M0 the null model. Null model, this is a model with zero predictors, okay? The simplest model you can have. It's a model that says y is basically a constant, beta 0. You can still have an intercept, okay, but this doesn't count as a predictor. It's just a, well, just a constant. It doesn't depend on the predictors, okay? Plus the error, okay? So that's your null model. Now, for k goes to 1, 2, up to p, and basically this language for k equals 1 to p means that those steps, you will repeat both of them for every k. So you first do it for k equals 1, then you do it for k equals 2, then you do it for k equals 3, up to p. Now, first step, I should say, is to fit all k and p models that contain exactly k predictors. Well, yes. Well, let's say we're at the first step, so k equals 1. Well, okay, choose, remember that this notation kp means k choose p. So it's a number of different ways you can pick k elements out of p elements. So remember your probability classes. If k equals 1, well, of course, you have p different models that contain exactly one variable. But then if k equals 2, then you have more models that have exactly two predictors. You might remember the formula. It's p factorial divided by k factorial, p minus k factorial. Okay, evokes nice memories from first year university, I hope. Okay, so the point here is you fit all of those models. And now you will call simply mk the best model with exactly k predictors. So remember, if k is 1, you had p models. To fit, you pick the one that is the best. Best how? Well, simply based on R squared or equivalent. So the bigger R square, of course, is the better, or equivalently, the smaller RSS. Okay, so you do that, it gives you your MK model. So of course, you're going to get M1, you do it again, you get M2, you get M3, and so on. Of course, M3 just means best model that has 3 predictors, and so on. MP, well, MP is trivial because it's the model with all the predictors. And then lastly, well, you're just gonna select the overall best model amongst M0, M1 up to MP. So because now you have, I suppose, P+1 candidates, you have those new metrics or new criteria you've developed, AIC, BIC, blah, blah. You pick your favorite one. You say, okay, I really like the BIC, so I'm going to pick all of those M0, M1 up to MP. I pick the one that has the lowest BIC, and that's it. Job done. That's my best model. Okay, I hope that's relatively simple. Maybe it's all a bit verbal, is just to say overall, what you end up with is the model that has the best criteria based on your favorite criteria. Here we have a question for a champion. So question for a champion, in step here 2B, we said to use to compare those models using the R squared, right? To pick the one that has the highest R square. But if we said before that R square is kind of flawed, why do we use R square here? So that's a question for a champion. Take a second to think about it. Let's see if you can be proven to be a champion. Well, the answer is simply that within those 2 steps, the number of predictors is fixed, right? So among all those K choose P models, well, they all have exactly K predictors. So you don't need to adjust for the number of predictors. All those models here, they have the same number of predictors. So it's totally fine to use R squared to judge which is the best. Well, they all have the same number of predictors. Okay, so all of this sounds great. But we've swept the potential problem under the rug. I think you guessed it before, maybe you've guessed it before. It might be infeasible to fit all models, okay, because there's potentially a very large number of models. Okay, even if the number of predictors is, maybe not small, but moderate or moderately large, it's a lot of models because in total, that's the number of models you fit. Well, yes, because you fit, 1 choose P, 2 choose P, 3 choose P, blah, blah. You sum all of those numbers, that's actually 2 to the P models. Okay, so you're fitting 2 to the P models. Imagine that P is 100. Well, 2 to the 100 is a crazy number of models to fit. It's infeasible in practice to fit all of them. Okay, so sometimes if the number of predictors is too large, you simply cannot do best model selection. Well, unless maybe you have a couple million years ahead of you to do that. But for us, mere mortals, we will need some sort of second best approach, okay? Which is, there's a few available choices. The forward selection, we explain in some amount of detail, and then we just say a few words about backward and hybrid selection in those slides. So forward selection. So again, it's an alternate approach to the best subset algorithm. And here, spoiler alert, the forward selection will not necessarily give you the best model overall, but usually it's going to give you a pretty good one. It might give you the best, but there's no guarantee it will. So what is this forward stepwise selection? Well, here the algorithm, let's explain. Once again, you start with the null model. Once again, you're going to do a step for all the k's from 0 to p minus 1. But what is now the step? Well, you consider all models which add one predictor to the previous best model MK. So you start at M0. Okay, that's trivial. There's no predictors. Now you're going to add to this null model one variable, and you have in general p minus k such models. Okay, if k is 0, you have p models you need to try. Well, the model with the first predictor only, the model with the second predictor only, and so on. After that, so you have now, in this step, you have p minus k models. You choose, again, the best. Okay, the best among those p minus k models. Same thing, just based on R squared, the highest R squared. And then you call this best model the mk plus 1 model. Well, again, if you start at M0, you're going to get M1. Well, M1 is, of course, just the best model that has exactly one predictor. But of course, this is like a for loop in programming terms. So once you've done this step, you go back here, you go to k equals 1, and then you're going to add one predictor. So now you have chosen one predictor, you're going to add one more, and you're going to get, so then you have p minus 1 models to evaluate. And among those p minus 1 models, those with exactly two predictors, you keep the best one. And you call this M2. You do this again, 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 again. So lastly, you again get a few different choices. So M0, M1, up to MP. And you will simply pick the overall best, again, based on the criteria of your choice. Okay, AIC, BIC, adjusted R-square, and so on. Obviously, in this step, now it's important to use a proper metric, not just the R-squared, because all those models, they have different number of predictors. So we need to adjust for the size of the model, the complexity of the model. Okay, I hope that's relatively clear. In case it's not clear, what's happening here is we're not going to explore all the models because we have the pretty important restriction that all we do in this step is to add one variable, but the ones we've already picked, they stay there. They cannot be removed. Okay, that's the big restriction in this approach. We have a set number of predictors already chosen, and here we're going to add one variable, but then we cannot remove variables. Okay, MP, as you guessed, is the full model, the one with all the predictors. Okay, so here, even though we might not get to the overall best model, obviously this approach has the advantage of computational simplicity. So if you make the calculation, you'll see that the number of models we fit is this sum. Well, yes, because at each step, that's the number of models we fit. So basically, if you make the calculation, you get to this. That's the number of models. It is much, much, much smaller than this number here. Well, yeah, because it's basically proportional to p squared. Okay, well, this is 2 to the p. And so, yes, we've traded the absolute best approach for, well, a way that we can actually do it in practice if the number of predictors is moderately large. We do not describe here the backward stepwise selection, but frankly, if you haven't understood the forward stepwise, backwards is the same logic, but obviously in reverse. You would start with MP, and then at every step, you will remove exactly one variable. Remove exactly one variable, keep the model with one variable less that is the best, and so on. And then at the end, you still get a list of models that you pick the overall best based on your favorite criteria. Okay, so obviously, there's a big assumption here that those methods make, which is that it assumes the best model with k predictors is always a subset of the best models with k plus 1 predictors. Well, yes, it assumes, okay, if I have now k predictors, it's necessarily the case that the best with k plus 1 will just be the one that I add, but to which I add one. Or in the other direction as well, if I start with k plus 1, that's my best model with k plus 1 predictors. The best one that has only k will be this one to which I remove one variable. In other words, these methods only look one step ahead. Now, in reality, there is no guarantee this is true. Okay, there's no law of the universe that says this must be true. So, as I said, there is really no guarantee that forward or backward selection will yield the absolute best model, but they generally lead to a decent one. Okay, and lastly, I mean, not going to explain much about this, but hybrid approaches exist. So these would be some sort of improvement on the backwards and the forward selection, which at each step it's allowed to both add a variable or remove a variable. So those would be an improvement on backward and forward selection, and yet they're still not perfect. They're still not as good as the best selection approach. Now, just to conclude, and here you need to trust that this example is true from the book, but in the data set in the book, they actually make the point that best subset selection does not lead to the same thing as forward stepwise selection. And let's just explain the logic here. Those are all the steps of both algorithms, right? So this would be the result of getting the best model for one variable, so M1, M2, M3, M4. Now, when you use best subset for one variable, you get the following variable rating. So that would be the best variable. And you get the same thing for forward stepwise. Whoa, I get some problems. When I get to the end of the video, I suppose I get more tired and I cannot speak anymore. So rating, the same. Now, if you go to two variables for best subset, rating, income, it's pretty good. Forward finds the same because, well, rating income, that's the best with two variables. Well, all you need to do is add income to rating. That's great. So forward is going to be able to find that. The best model with two variables. Best subset for three variables would be rating, income, student. So that's great because again, you start with the same two. All you need to do is add one. And so rating, income, then you add student. Forward selection is capable to do that. But here's the catch. Now, with four variables, the absolute best model would be, well, you see rating has disappeared. So it's income, student, but now we have two new variables. So we have cards and limit. And forward selection is not capable to select this model because again, the only model that forward selection is capable to find is a model in which you start with those and you add a third. In which case, well, yes, we do add limit, but we're not capable to remove what was it, rating here. So rating stays in the model, and then you have income student. So basically, that's the illustration of what I said. The absolute best with four variables is this one. Forward stepwise as not founded, which is a bit sad. Anyway, I believe that's the end of those slides. Yes, so I will make a different video for this last section for multiple linear regression, potential issues with linear regression. For now, I thank you very much for your attention, and I hope to see you soon in class or in the next video.